Hello, everyone. I'm Dr. Wenzhen Li from Iowa State University. I'm happy to give my talk on electrochemical fixation and upcycling of nitrogen in extreme environments and food deserts in this NSF workshop. As we all know, industrial synthesis of ammonia from its elements is the greatest invention in the 20th century. It is the single most important change affecting the world's population. Its expansion from 1.6 billion people in 19th centuries to today's 7.64 billion would not have been possible without the synthesis of ammonia. Currently, ammonia synthesis is at a scale of over 150 million tons per year and predicted to rise 3% every year to fulfill global food demand. However, ammonia synthesis is under harsh conditions and it requires molecular hydrogen. Ammonia industry consumes 1% of global energy supply, contributing to 1.4% of total carbon dioxide emission. The centralized production limits transportation to some geographically difficult regions. With more and more renewable electricity being generated from wind turbines and solar panels, we're looking for more sustainable and cost-effective ammonia synthesis methods. Nitrogen is reduced by water to produce ammonia, which can operate under mild conditions. It is easy to downscale. The electrochemical processes can be decoupled from fossil fuels and reduce transportation cost of hydrogen and ammonia due to its distributed and flexible feature. Electrochemical nitrogen reduction reaction, also called ENR, has been emerging to a very hot research area. As you can see, the publication numbers shoot in the last 3 years. Different type of electrochemical cells, including H-type half cells, molten salt cells, MEA-based flow cells have been extensively studied. Although high production rate and Faraday efficiency using these cells have been reported, vigorously examining the true nitrogen source was also be proposed, questioning the capability of current ENR technology, especially for those with low temperatures and pressures with water phase electrolyzers. The control experiments with identical conditions, including electrolysis conditions and quantitative product analysis, should be applied to both argon and 15 nitrogen as feeding gas, as well as 14 nitrogen. These control experiments should be served throughout the whole study as routine factor checkers. Partly due to the early research stage, the ENR research is often plagued by the unexpected presence of reactive nitrogen species. Recent reports have identified fixed nitrogen sources such as nitrate or nitrite in commercial available electrolytes and electrocatalysts. Research efforts on identifying and eliminating reactive nitrogen species are playing a critical role in helping researchers avoid false positive results and unexpected pitfalls. However, if we just simply compare the bonding energy, we can see that the nitrogen triple bond has a super high energy, over 945 kilojoule per mole, much higher than other nitrogen chemical bonds. So this also indicates the direct electrochemical synthesis of ammonia, or ENR, using molecular hydrogen under low temperatures and pressures is very challenging. Therefore, we propose our visions for sustainable nitrogen fixation and upgrading in extreme environments and food desert regions. First, we can use renewable hydrogen generated from water electrolyzers powered by renewable electricity for small-scale Haber-Bosch reactor to produce ammonia. As you can see, hydrogen generation from electrolyzers consumes the most electricity, indicating future water electrolyzers need to be further optimized. But this route has been demonstrated in the East Iowa farm. The carbon neutral ammonia has been produced through this route to power their farm tractors. It seems that lithium-mediated ammonia synthesis and low energy cost non-thermal plasma fixation of nitrogen gas to get nitric or nitrous acids, and then reduce these higher chemical state nitrogen species back to ammonia are two feasible routes. These methods can be powered by renewable electricity generated from wind turbines and solar panels and have been confirmed to be able to activate nitrogen gas to ammonia synthesis. However, their costs need to be further reduced and the process further optimized. We also envision that the NOx can be obtained from agricultural or industrial waste streams and serve as important precursors for production of other higher valued nitrogen chemicals such as hydrazine amine and hydrazine, and even further combined with greenhouse gas carbon dioxide reduction for synthesis valuable carbon nitrogen chemical distributedly. Finally, I would like to acknowledge my collaborators from Iowa State University, Wichita State University, George Washington State University, and the founding source from RPRE, NSF, and the state of Iowa. I would to thank NSF again for organizing such a wonderful workshop.